Now let's consider steady state processes where flow can enter and leave the control volume. We're going to move from the concept of just a closed system and energy interactions to an open system where mass can flow in and out of the control volume in an open system. So, for example, if we have this open system, then the system itself is the area denoted by the pink rectangle. And if we have 7 kilograms of mass come in and 2 kilograms leave, then the system must have gained 5 kilograms. Just like if you go to your bank account, you deposit $7 and you spend $2, well, then you've increased your bank account by $5. It's the same thing, but we're considering energy that enters and leaves, or mass that enters and leaves, rather than money. So we need to talk about conservation of mass. Now, we're not going to explore the conversion between mass and energy, Einstein's equation. I don't know enough about that to talk about it intelligently, and quite frankly, we don't need it for what we're doing. A lot of times what we're interested in are situations where mass and energy are conserved, which is 99.99% of everything we do as engineers. So we're going to consider mass and energy as separate things, both being conserved. So it works just like a bank account does. If you have mass flowing in and mass flowing out, then the net change in the system is the difference between those two flows. So as I said before, if I put more mass in than I take out, then the amount of mass in the system goes up. If I take out more than I put in, the mass in the system goes down. So it's a pretty simple thing. And there could be multiple inlets. That's what the I stands for as a subscript. There could be multiple exits. That's what the E stands for. And the subscript CV stands for the control volume. What the mass balance says then is that all the mass that flows in minus all the mass that flows out equals the change in mass inside of the system or inside of the control volume. So to understand mass flow rate, we need to consider it in a little more detail. If you think about a pipe, just a simple round pipe with liquid flowing through it, we could take that pipe and look at it from the side. There would be a certain amount of cross-sectional area, which if it's round is easy, is just pi d squared over 4. And if you know much about flow, you know that actually the velocity of flow depends on how far away from the side wall you look. So it turns out that fluids typically stick to the side walls of pipes. And so if that's what happens, then the velocity of flow at the sidewalls is 0. In other words, touching the pipe is a 0 velocity flow. But as you move more and more towards the center of this round pipe, especially if we're talking about something like laminar flow, then in the center of the pipe you'll find the maximum velocity. So in other words, the actual velocity varies across the entire cross-sectional area of flow. And in order to calculate the mass flow rate, what we'll have to do is integrate the velocity of flow over all the small differential areas and then multiply that by density. If you think about the units, it makes sense. If you want mass flow, well, that's mass per time. So if you multiply density, which is mass per volume, times a volume flow rate, which is volume per time, well, then you'll get mass per time out of that because the two volumes will cancel in the denominator of the density and in the numerator of the volumetric flow rate. Now, since we want to talk about velocity of flow rather than necessarily volumetric flow rates, then we need velocity of flow times area. And you can see that I've got a small differential equation that says the differential amount of mass that flows through per unit time, that little dark blue rectangular area is equal to the density of the fluid flowing through that times the velocity of flow times that differential cross-sectional area, that little bitty square there. Now, if we want to get the total mass flow rate through the whole pipe, through this whole area, well, then we have to integrate that differential mass flow over the whole cross-sectional area. Now, this is a lot of detail, and most of the time we really don't care. Most of the time we don't care about the fact that the velocity varies depending on where inside the pipe you look. Most of the time what we want to do is use an average velocity, because then the density is pretty much the same everywhere. The velocity taken as an average is the same everywhere, and all we're really doing then is integrating over the cross-sectional area, which is just the cross-sectional area. So then the equation simplifies, and we don't have to integrate, which is nice. It simplifies down to the equation in the box that says that the mass flow rate in the pipe is equal to the density of the flow times the average velocity of flow multiplied by the cross-sectional area. So if you understand all of the reasoning behind this, that's fine. But what you really need to know is that we have an equation that relates mass flow rate through a cross-section to the velocity of flow in the cross-sectional area of flow. Now, what about volumetric flow rate itself? Sometimes that's what we really care about, because sometimes we don't really want mass flow rate, we want volumetric flow rate. That can be very interesting and useful in a lot of problems. So what is volumetric flow rate? Well, it's just volume per time rather than mass per time. So rather than integrating the density times the velocity of flow times the differential cross-sectional area, what we'll do instead is just simply integrate the velocity of flow over the whole area, and that will give us the volumetric flow rate. Or in other words, how many, you'd probably think of it in terms of gallons per minute pass a particular point in the pipe. So again, we'll make a nod to the fact that the velocity of flow actually varies along the entire cross-section, but we'll take an average velocity, just multiply that by the cross-sectional area, and call that then the volumetric flow rate. So here's an equation that relates velocity of flow to volumetric flow rate. Now be careful, we've got a whole lot of V's running around in this course. I try to use a script V for velocity. I use a capital V for total volume. I use a lowercase v for specific volume. And if I have a dot above it, that means per unit time. So this capital V with a dot above it just tells you a volumetric flow per unit time. So think of it in cubic feet per second, or like I said, gallons per minute. Volume per time, in other words. Now, there is a relationship between the mass flow rate and the volumetric flow rate. You might notice that those two integrals look a lot alike from the last slide, and that's because they are related. Usually the density does not vary along the entire cross-section, and so we could simply factor it out and note that the density times the volumetric flow rate is equal to the mass flow rate. Now remember that density is the inverse of specific volume, and so volumetric flow rate divided by the specific volume is the same thing as density multiplied by the volumetric flow rate, since again density and specific volume are inverses of one another. So now we can talk about an energy balance for an open system. Before, when we had a closed system, no mass crossed the system boundary, so it was pretty easy to keep track of energy flowing across the system boundary, because the only two forms we had were heat and work. So heat could flow into or out of the system, work could flow into or out, and remember we defined heat in and work out as both being positive quantities. However, now that we have mass flowing in and out of the system, that mass can carry energy with it, and there's a couple different forms we have to recognize. So in general, our energy balance for an open system would be as follows. The total energy crossing the boundary is heat and work, whether it's going in or coming out. That's that first term. We already know how to deal with that. Plus the total energy of the mass entering the control volume minus the total energy of the mass leaving the control volume is equal to the net change in the energy in the control volume. So this works just like a bank account too, except that it's considering flows instead of cash flows, right? This is mass and energy flows, or essentially the energy that mass carries with it. So if the mass carries energy in, that's like a deposit into your bank account, just like heat or work can deposit energy into the system, but those things can also carry energy out. So both mass, energy, and heat, all those can carry energy out of the control volume, just like a withdrawal, right? You can go spend money at JCPenney's, you can go spend money at Walmart, you can go spend money at the gas station. All those things withdraw money from your account and change your account balance. So our account balance is basically just all the energy in the control volume, and it can go up, go down, or remain the same depending on what particular type of process we have occurring. So to write that out in a symbolic form, we have Q minus W, just as we had the sign conventions before. Heat in is positive, work out is positive, and that's the Q and the W piece. But remember, there can be multiple heat flows and multiple work flows, so I probably should have included a summation sign in front of the Q and the W in this equation. Similarly, there can be several different mass flows into a system. If you think about taking a shower in the morning, for example, you turn on the hot water and then you dial in the cold water in order to get the temperature to a comfortable temperature for your shower. Well, do both of those streams carry energy in? You might be tempted to say, well, only the hot stream carries energy in, but if you think about it, the cold stream is above a temperature of absolute zero. And so while it doesn't carry as much energy in per unit volume or per unit mass as the hot stream does, it still carries energy in. So both of those streams are coming into a mixing valve and carry energy into that control volume, if you will. And then there's only one outlet that comes out through the shower head or bathtub if you're taking a bath. And so that's a single exit, but there could be multiple exits. What if you had a leak, for example, right? Then you'd have two different flows at least of water coming, well, maybe only one. You might only have water coming out the leak. But the point is that energy can be carried into or out of the system, not just by work and heat, but also by multiple mass flowing streams, and those will change the amount of energy in the control volume. Now understand, we're not talking about a rate, we're just talking about an amount of energy being carried into or out of the control volume. Now there's a form of energy you need to know about, and I'm going to try and describe it to you and help you understand it intuitively, but it's the real reason that we have the property called enthalpy, which is a combination of properties. Consider a control volume that has mass flowing into it. By now you're probably comfortable with the idea that there's this thing called thermal energy. You used to probably think about that essentially as heat or as temperature, but really it's thermal energy. It's the molecules moving on the molecular scale, and that internal or thermal energy, which is the piece we really care about, is the thermal piece. We give that the symbol U. So if we have a control volume and mass is coming in, that mass will carry thermal energy with it. That's U1. It'll carry thermal energy out. If there's a flow out, that's U2. So that's pretty easy at this point. But doesn't the incoming stream have pressure? It does. In fact, doesn't the control volume have pressure? Think about a simple example. Think about something like a water heater in your home. Okay, so this water heater has water coming into it. Have you ever measured the pressure of the water in your pipes? Did you know that it's anywhere from about 50 psi to about 80 psi? It's a decent amount of pressure, right? So if the water heater is under pressure and you're trying to push more water into it, well, that's going to take work, right? In fact, let's call it a packet of water. You can see it there in pink in the middle upper figure. That packet of water has some pressure and has some specific volume, and basically it's going to be pushed into the control volume under pressure. So you can see it before entering in figure A and after entering the control volume in figure B. Now something has to push that in. In other words, something has to apply force through distance to get this packet of water into this pressurized water heater tank. Okay, so what is it that does that? Well, it's the fluid upstream of this little packet of water, right? So we could consider that water that's doing the pushing as sort of like a piston that is pushing this little packet through a distance. Now let's put some more symbols around this packet. We'll have a volume V, a pressure M, a certain amount of mass M. I don't know how much mass there is. It doesn't matter. It depends on how big of a packet we take. Let's just make this up as we go. Why not? And then the length that we have to push it in, of course, is related to the volume and the mass and the density and so forth. But we're going to have to push this packet a certain length in order to get it into the control volume. Now let's think about this imaginary piston and the work that piston is doing for a moment. If we consider that piston, it's as if the water is applying a force. The water upstream is applying a force to our little packet in order to push it in. And the pressure, the back pressure if you will, acts on the surface of this piston across an area A. So we can actually relate the force to the pressure and the area. As a matter of fact, the amount of work done by this force is F times L, right? There's a force F that pushes this packet through a distance L. Well, that's work, right? Because force times distance is work. But the force being applied is pressure times area. So in our equation down there, our flow work is F times L, which is equal to the pressure times the cross-sectional area times the length that the packet gets pushed in. But the area, if you think about it, the cross-sectional area of the piston multiplied by the length is actually just the volume of our imaginary packet of water that we're pushing in. And so the flow work for getting this packet into the water heater is just P times V, right? It's the pressure that packet is under times the volume of that packet. Now, of course, the amount of work that it takes to push this packet in depends on how much of it there is, right? The bigger the packet, the more work it's going to take to push it in because there's just more of it. And we don't usually like things that depend on the extent of the thing we're considering, in this case, this packet of water. So what we're going to do is say, well, we know the mass of the packet, at least we wrote it down, right? It's related to the other variables. So couldn't we divide the flow work for the whole packet by the mass in the packet so that now we have the specific work? In other words, how much work it takes to push 1 unit mass of this water into our control volume or our water heater. So now we're writing the flow work with a lowercase w, indicating the specific work or the work per unit mass. And of course what that does to our PV product is just takes the volume and changes it from a total volume to a per unit mass volume, or what we've already discovered and called a specific volume. We don't mean a particular volume, we mean the volume per unit mass, or in other words, the inverse of density. So we recognize now that this water or fluid or whatever it is that comes into a pressurized container has two forms of energy in it. It carries in not only internal energy, which is the thermal energy primarily, but also it carries in flow energy, and we can't neglect that, because if the pressure of the outgoing stream is different, well, then there's going to be a different amount of flow energy carried out than was carried in, and we need to be aware of it. So this is actually the reason that enthalpy was defined in the first place, is to combine these two things that appear so frequently with mass flows, this thermal energy contribution and this flow energy contribution, together into one convenient thing that is in fact a property of the liquid. Because think about it, the pressure and the volume are properties of the fluid that's coming into the control volume. And so it's a capital H is defined as capital U plus P capital V, where this is talking about the total enthalpy of our fluid packet, which consists of internal energy for that whole packet plus P times V, flow energy for that packet when it's pushed into the control volume. Of course, we can write this on a per unit mass basis as little h equals little u plus P little v, where we've got the internal energy, or the thermal energy, really U, and PV. I keep saying internal and thermal energy, and I go back and forth between the two. There is technically a difference. The difference is that internal energy is the sum of the thermal energy plus the chemical energy that the particular fluid brings in, whereas thermal energy is just the temperature piece, if you will, okay? So really, I should be saying thermal energy for all of this, because a lot of times we don't have any chemical reactions going on, and so we don't have to consider the chemical energy piece in that contribution. Now, an interesting sort of popular culture reference here, though it's a fairly old reference, there was a movie by Disney way back before I was a kid. It was in black and white. It was called The Absent-Minded Professor. If you ever get the chance to watch it, you should. It's a good, clean family movie. You can watch it with a 3-year-old and not have to worry about there being anything to really scare them or scar them for life. It was interesting because this is a professor, and he's teaching all these science things, and he's excited about everything, and his students don't understand where he's going, and he's got his head in the clouds. He's forgetful about everything. And he has forgotten his own wedding 2 or 3 times already. Why his fiance continues with him, I'll never know. But anyway, so they're supposed to get married, and you know, this is kind of the backstory that he's forgotten a few times. And he goes to his workshop and he realizes he needs to get ready for his wedding, but he also has just had a sudden inspiration. He looks at a chalkboard that he's got in his lab, and it has this equation, H equals U plus PV. And he looks at it and he makes up all this gobbledygook. I'm sure it was written in the script about, oh, if I don't worry about the whatever throwing off extra gamma rays, it'll all be okay. And he changes the plus to a minus, and so he changes some dials on his chemistry setup, and you know, there's all this fake 50s scientific sounding popping and things going on in the background. And of course, what ends up happening is an explosion, and he's knocked unconscious. He misses his wedding yet again, right? And so then he kind of wakes up in the morning. The roof to his workshop is pretty much gone. Daylight streaming in. I think his dog's even licking his face to wake him up. And he looks around and he sees that, no, it didn't work. And he goes back to the blackboard that's kind of at an angle down. He just kind of sighs and changes it back from a minus to a plus. Well, it's interesting that they use this equation because it's actually just a definition of enthalpy. So it was kind of appropriate for the movie, because what ends up happening through that accident, of course, is that he develops a substance that generates its own energy. So he picks up a glob of it, makes a ball out of it, and bounces it, and it bounces higher and higher instead of lower and lower. And so he realizes it's generating its own energy. So this is basically an over-unity device, which we believe is impossible. You tried to build a perpetual motion machine, so you should know that it's, you know, it doesn't seem to be possible. In fact, energy conservation is one idea that has led us to tremendous discovery. If we ever find out that energy conservation is wrong, we're going to have to rethink a whole lot of things. Not a whole lot. We're going to have to rethink everything. But it was just interesting that they included this little thing that is related to energy in a movie that breaks essentially the first law of thermodynamics. So if you ever get the chance to watch it, I think it's worthwhile. Anyway, so now we realize that if a fluid is flowing, it can have more energy than if it's stagnant. So if we have a stagnant or non-flowing fluid, then not only can that fluid have internal energy, but it could have kinetic and potential energy. Now you might look at this and say, wait a second, if it's not flowing, how on earth does it have any velocity? Well, I have a pond, and I've had this pond stocked. It's got a pretty decent culture of fish, I guess, but I wanted some others, so I had them put in. Turns out there are laws against putting your own fish in the pond and different species and things, which makes sense. You don't want them to get out and decimate local, natural, or I should say, what's the word for it? Just populations of fish that normally are there, right? Sort of indigenous to the area, if you will. So the people that came and put fish in my pond, they had a large tank on the back of a pickup truck essentially, maybe a half ton or a ton pickup truck. And if you think about that fluid, it's not really flowing around, but as they go around curves and as they're going, 50, 60 miles an hour down the road, that fluid certainly has kinetic energy. If you were to slam on the brake, you find out really quickly how much kinetic energy that fluid has. It's not a flowing fluid, it's not flowing through pipes, but it is moving and therefore has kinetic energy. It's also sitting up on top of a truck bed, so if they were in a wreck and the thing slid off the side, you'd realize that it also has potential energy. So it's possible to have a non-flowing fluid that has thermal energy, or internal energy, as well as kinetic and potential energies. If you have a flowing fluid, think of a pipe that's elevated in the air, then it's pretty easy to see that because of the motion of the fluid relative to ground, it will have kinetic energy. It also has potential energy. I kind of made this up, right, because I raised the pipe above the ground, but certainly it does have potential energy. And now it will also have internal energy and flow energy because it's a flowing fluid that is being pushed against some pressure. And so here we see that in this flowing fluid, the combination PV and U would be put together to indicate an enthalpy. So for a flowing fluid, we give it the specific energy symbol of theta, which that adds together the enthalpy, the kinetic energy, and the potential energy. But for a non-flowing fluid, we'll use the symbol lowercase e to indicate that it's not flowing and therefore does not have any flow energy. Now, an interesting process is the steady flow process. There are a whole lot of devices that operate at steady state or very close to it that are very useful in our everyday life. And I'll show you some in just a little while, but we need to consider steady flow processes where instead of the mass and the energy in the system changing over time, they simply remain constant. This may be a lot like your bank account. It may seem like it tails off, but unless you're filing for bankruptcy, your bank account probably stays pretty level at one number unless you're very careful and saving money, very stringently. So as mass flows into the control volume, the same amount needs to flow out so that we have a steady flow process. So this would be like saying you've got, I don't know, maybe you have an emergency fund of $1,000 in your bank account plus $500 for incidental expenses, and every time you get paid, it seems like you just kind of hover around that $1,500 mark because you have to spend money to eat and to, go to school or whatever things that you do. And so it seems like that the balance of the money in that account just stays steady over time. Well, that's essentially what we're doing here, except we have two different things that are staying steady. We've got mass that remains steady and energy that remains steady within the control volume. Now, if you think about what happens in this, what that means is that mass might come in carrying with it energy, or remember this is a pressurized container most likely, so enthalpy, and then streams could leave carrying enthalpy as well. Now a lot of times, notice that I said enthalpy and I didn't mention the other two pieces. I didn't use theta even though these are flowing streams. Why not? Well, much of the time the flow energy and the internal energy are much larger than the kinetic and potential energies of the streams that are flowing into or out of our control volume. So if you think about water again flowing into your water heater, it turns out that the thermal energy coming in is usually much, much larger than the kinetic energy or even the potential energy. Water usually flows into a water heater from the top, so you could consider it as having potential energy, but the amount of potential energy it has is practically nothing by comparison to the thermal energy. As a matter of fact, there's a little calculation you can perform that it will help you understand how important thermal energy is. Think about this for a minute. If you have a pound of water, okay, so a pound is not a whole lot. You could lift a pound pretty easily. Somehow you're holding a pound of water, And let's say this water is at, I don't know, 70 degrees, okay, and you hold it for a while, and maybe your hands give enough energy into that water so that it goes up from 70 to 71 degrees. It just increases by a measly 1 degree Fahrenheit. Did you know that the amount of energy that's gone into that 1 pound of water, if you took that energy, instead of making it go in as a temperature rise or a thermal energy change, did you know that that same amount of energy could raise that pound of water into the air by 778 feet? Now that's a pretty decent height. I don't think I could throw a pound of water 778 feet in the air, but I bet that my hands are warm enough that I took, let's even say a 60 degree pound of water. I bet that after a while my hands and my body heat would warm that water up by a degree fairly easily. It might take a while. My hands might feel cold when it's done, but that's doable, right? And so hopefully that gives you some respect and some insight to the amount of energy there is in thermal energy for even very small changes in temperature. And there's actually fairly large changes in thermal energy for changes in phase. If you think about steam condensing into liquid, that's quite a bit of energy per unit mass. So a lot of times the internal energy dominates the other forms, right? Because there can be flow energy, there can be kinetic energy, there can be potential energy. Potential energy is usually the smallest part. Kinetic energy is the next. After that is the flow energy, and then thermal energy is by far and away usually the biggest contributor to the energy that mass either carries into or out of a control volume. So that's considering the energy flow in a steady flow process, but also the mass would have to be steady. So if we have, say, 2 kilograms per second coming in one port, 3 kilograms per second coming in another, we must have 5 kilograms per second leaving. So the rate of mass flow in from all ports equals the rate of mass flow exiting from all ports. And that would be our steady flow mass balance. For a single stream, we would have one single inlet and one single exit, and your water heater is an example of this. You're probably pretty happy to have a water heater. If you've ever had to take a cold shower, you probably wished your water heater was working, and your water heater has a single inlet for cold streams and a single exit for the hot stream. It's a very useful and comforting device. And the amount of water in the water heater doesn't go up and go down. It's just filled with water all the time. So if some water comes out for you to take a shower, then water has to flow in at the same time. And that's why the water in your water heater gets cold fairly quickly. They actually design them carefully so that hopefully the water exiting doesn't mix much with the water coming in. But eventually you run out of hot water. There's still water in the tank, but it's cold water because it's fresh water coming in from the city supply or wherever you get your water from, maybe a well or something. But for a single stream, the mass flow rate entering and leaving, or the rate at which mass enters and leaves the control volume, is equal to one another. And since mass flow rate can be written in terms of density, velocity of flow, and cross-sectional area of flow, then what that means is rho 1 V1 A1 equals rho 2 V2 A2, where those V's are velocities of flow. This is an equation worth writing down. It is in Chapter 4. You should either go and highlight it or go to the back of Chapter 4 at this point right now, where the summary equations are, and write it down. I'm pretty sure it's there for a single inlet, single exit stream. And this is just the mass balance. Now remember, a steady flow process has the same amount of energy entering per unit time as leaves. So we'll get to a steady flow energy balance in just a minute. But this is the mass flow piece. Now, we can also write this equation in terms of specific volumes. You'll find in this class that we prefer to use specific volume instead of density. So again, density is just 1 over specific volume, so we can make that substitution. It's the same equation. But again, if the back of the book doesn't have one of these two in the summary, you should add it in. I bet it has one or the other, maybe not both, but you should make sure both are there. They're the same equation. It's just, in the stress of an exam, you may not think of the fact that density is the inverse of specific volume. So how about energy that is transported by mass? What's the rate at which energy is transported by mass? Well, now if we have a mass flow rate of fluid coming into the control volume, and we know that each unit mass carries a certain amount of energy with it, then the product of those two represents power input to the system by mass. Now this can be a little bit confusing at first, so think with me back to some old Western movies, okay? There's a couple things that always happen in old Western movies, right? Either there's going to be a train robbery, or there's going to be a prison break, or the good guy's going to go to jail, or maybe something's going to catch on fire, right? That seems to happen. It seems like all Westerns have one of those elements, or you can't hardly call it a Western. So what about when things catch on fire, what happens? Well, back in the old days, fire trucks were fairly rare, hydrants even more so. And so what do you do when you're, 20 people in a little bitty town out in the western frontier and something catches on fire? Well, you form a bucket brigade, right? So you form a line of people, and maybe there's a well, you're drawing water from the well, and rather than everybody getting tired and running to put buckets of water onto the fire, you just pass the buckets down the line and pour it on the fire, and then have a return line for the buckets and hopefully put out the fire. That's the way I want you to think about this. Think of the mass, each unit mass, say each pound or each kilogram that comes in, as sort of like a bucket that carries energy. The amount of energy that bucket or that unit mass carries is theta, right? Maybe it's some internal energy, some flow energy, some kinetic energy, some potential energy, of course primarily it's thermal energy, right? But all those things are captured in theta. So theta is kind of like how much the bucket holds, how much energy it holds in all of its forms, and then m dot is the rate at which those buckets are going to the fire. And the product of those two then is the flow rate of water onto the fire. I hope that analogy helps you understand how mass carries energy into the system per unit time. So to write that out in equation form, the power input or exiting even a system by mass is equal to the mass flow rate times theta, because this is a flowing stream, and we can break up theta into its enthalpy, its kinetic energy, and its potential energy. And like I said very often, we will neglect the kinetic and potential terms, and so the energy or the power carried by mass is simply the mass flow rate times the enthalpy. So finally, let's approach our steady state balance, our steady state energy balance. We've seen the steady state mass balance, but what about energy? Well, here it is. If there's no accumulation or depletion of energy within the control volume, then what that means is there's no change in the account balance per unit time, right? However much energy is in there is how much there is in 2 hours later, right? It's just a steady flow system. So if we write a rate equation that is tracking the rate at which energy is carried into or out of the system, then we'd write Q dot, the rate at which heat carries energy into the system, minus W dot, the rate at which work carries energy out of the system, equals the sum of all the mass flow rates that are exiting times the internal energy, total specific energy that those streams carry. That's the theta here, minus all of the streams that are coming in, the rate at which that mass is coming in, times the amount of energy each of those streams carries per unit mass, okay? So all we've really done, this looks like a complicated equation, but it's really not. It's just all a bunch of deposits and withdrawals, but not deposits and withdrawals that are a one-time thing, but that are a continuous thing, okay? So we've got basically money flowing into and out of our account continuously in this balance, and the amount of money in the account never changes with respect to time. Now the forms of the deposits and withdrawals are work, heat, well I should say it in order, heat, work, and mass flow. Understand that heat really should have a sigma in front of it as well, because you could have heat flowing into the system, you could have heat flowing out of the system at some rate, you could have work flowing into the system at some rate, work leaving at some other rate, right? In the same way that you could have multiple mass streams carrying energy into or out of that control volume. All these things are continuous deposits and withdrawals. So if we expand that theta into all of its glory, right, expand it out into its enthalpy, its kinetic energy, and its potential energy, then we can write the equation as you see in the box. Again, if you understand all this, that's good. I think it takes a little while working with this equation to understand what all of the terms mean and what goes where. But this is a very important equation. That's why I put a box around it. You should go to the back of your book and see if it, not the back of the book, the back of the chapter, and see if this equation is listed. If it is, it's worth putting a highlight or a note next to, because this is a very important equation. Now, if we have a single inlet and a single exit, which will happen quite frequently, then we don't need summation signs in front of the mass flow rates, right? Because there's just a single inlet and a single exit, and then we can combine the thetas from the single inlet and single exit, because if you think about it, for the system to be at steady state, the mass flow rate in has to equal the mass flow rate out. So we just got one mass to flow rate to talk about, and that's m dot. And so we can combine the enthalpy entering and leaving, take the difference between the two, kinetic energy entering and leaving, and potential energy entering and leaving. So here's another important equation, but this one's only good for single inlet and exit systems. Now, a lot of times we really don't want to talk about the mass flow rate or have to use it. So what if we take this equation and divide it by the mass flow rate? What would happen? Well, on the left-hand side, we'd get Q dot over M dot. What would that really mean? Well, Q dot is a heat flow rate. Let's just think of it as heat flowing in. That'll make it easy, okay? So heat flow rate coming in divided by the mass flow rate coming in. We're not saying that that mass is carrying energy. Well, let me back up. We're not saying that that mass is carrying heat in. This heat could be flowing across a sidewall somewhere else, away from where the mass is coming in. But this ratio is still important because it tells us how much heat comes in per mass that comes in. There may be no real relationship between the two, right? But if we have a heat flow rate of, I don't know, let's make the numbers easy, a kilowatt, so 1,000 watts, so 1,000 joules per second coming in, and we've got mass coming in at a rate of 1 kilogram per second, well, it's pretty easy to see what little q is, right? Now, let's see if I remember my numbers. It'd be 1,000 joules per kilogram that comes in. So for every kilogram of mass that comes in, there happens to be 1,000 joules of heat that flows into the system. That's what that little q means. And the work is similar too. So we can write the Q and the W in sort of a per unit mass type of nomenclature, which is convenient quite often. In that case, all we've really done is taken the mass flow rate from the right-hand side of the equation and moved it over to the denominator of the left-hand side of the equation. So while this last equation does not have dots above the terms, it is still a steady flow, or it's a flow energy balance, okay? So remember, and you might want to find this one also in your summary in the back of chapter 4, and make a note next to this equation that this is only good for a steady flow system, and there is a rate going on here, but it just doesn't appear in the equation.